So let's move on to numbers. For numbers, I'm going to start by encoding 0 the same way as I encode false. This is much the same way that in C, the representation for false and 0 is kind of the same bit pattern. Here we're going to use the same function pattern. When I say that 0 is exactly this function, I don't mean that the names of the arguments matter. For example, if I change this argument to a name f and have y as a second argument, that's still the same function. It's still something that takes 2 arguments and returns the second one. And by convention, I'm going to tend to write f for 0, as we'll see, because I'm thinking of 0 as something that takes 2 arguments and applies the first one 0 times to the second argument. Whereas 1 will be similar. It's a function that takes 2 arguments, but it applies that first argument 1 time to the second argument. 2 applies the argument twice to the second argument, and so on. Here's 3. 3 f's applied to y. And when I say apply it 3 times, what I mean is I apply it once, take that result and apply it f to that, take that result and pass it again to f one more time. So for any number n, I'm going to nest applications of f in deep. And that is my encoding for numbers. That's fine. That means you can write down any number that you want, but how do we compute with those numbers? How do we add them, say? And the simplest thing we can try to do is just add 1 to a number. So let's see if we can define the function add1, which takes a number and should return a number that's 1 bigger. Since it's returning a number, the thing that it returns should have the shape lambda f lambda x. Right? This lambda n is taking the argument, and then we're returning a number, and all of our numbers take f and then x. Our goal then is to apply f to x n plus 1 times in the body of this function. We have n, and if we apply n to f and x, then that applies f to x n times. We're exploiting the particular encoding of numbers in order to implement add1. We know that n is encoded as a function that takes 2 arguments and applies its first argument to its second argument n times. So to apply it n plus 1 times, we just have to add 1 more application of f on the outside. And now we've implemented add1. We take a number and we return this function, which takes 2 arguments and applies f n plus 1 times to x by using the fact that n will apply n times to x. And we can check that add1 of 0 is in fact 1. If you have add1 of 0, then 0 goes in for n, and we end up with this function. And now we can simplify the inside of that function. If we expand the abbreviation of 0 out, then f and x are going to go in as the arguments, leaving us with just x, while we still have an f on the outside, and we got 1. We're going inside of functions and simplifying the body of the function before the function is called, which is not the kind of thing you do in the languages that we've been looking at and implementing. But in this minimal lambda calculus kind of world, that's the kind of thing we do because we're relying on functions as encodings. If you want to add 2 to a number, you can just use add1 twice. And if you want to add 3 to a number, you can use add1 3 times. But what if you want an add function that takes 2 numbers and adds the second one to the first one? Then you would need to use add1 m times for an argument m, starting with n. Fortunately, because we know the encoding of m, we know that m will take some function like add1 and apply it to some argument like n m times. So we can add m to n by starting with n, adding 1 m times. We're exploiting the encoding of numbers here to implement addition, and to turn that around, that's how we chose this particular encoding. The encoding, by the way, is called church numerals. And we could double check that add 1 and 2 ends up with 3, because add 1, the 1 and 2 goes in for n and m. That leaves us with 2 of add 1 applied to 1, which means that we apply add 1 twice to 1, which means we're going to get 3 out. You can play the same trick to multiply numbers. When you have n and m to multiply, what you want to do is start with 0 and add n m times. Right? Notice that add applied to n is a function that wants 1 more argument so that it can add n to it. But we can take that function and reuse it m times, starting with 0, and multiply m and n together. Again, we're relying on the encoding to implement multiply this way. How about checking for whether a number is 0? So this id0 function needs to take a number n and return true or false, keeping in mind that these are our function encodings of true and false. So how can we tell the difference between a 0 and all other numbers? Well, a 0 is the only one that never uses its first argument. That is, when we apply the number 0 to a function and an argument, it applies the function 0 times to the argument. So if we apply this function 0 times to true, we're just left with true. Where if we apply it one or more times, then we will get false back. For example, is 0 of 0, I should have an s there. The 0 goes in as n. We 0 times apply this function to true and end up with true. Whereas is 0 of 1 means that 1 is going to apply this function one time, which will give us false. And of course, if you keep applying the function that always returns false, you'll still get false, even for larger numbers. Notice that this is 0 test is not very fast. In order to test whether 1,000 is 0, it will do 1,000 function calls, keep getting false every time, right? But we're more interested at the moment at what is, in principle, can be encoded. And there are different kinds of encoding numbers, encodings for numbers that would have different properties and better performance. To finish up our arithmetic, we really need a way of subtracting. And subtracting is a little harder than addition. If we try to pursue the same strategy that we did for addition, then we take the number n and we apply it to f and x. Now we want to take back one of the f's. And it's too late. There's no way to take a function and do the opposite of the function. So we can't quite do this, although this idea is not far off. What we need to do is keep some pairs of the number that we're working on and the previous value that we have. So instead of just adding 1 n times, we're going to take a pair, we're going to remember the second part of the pair and add 1 to it to get the second part of a new pair. And then we'll do that again. The second part of the new pair is remembered and also added 1. So that after we do this n times, we're going to end up with an n as the second part of the pair, and we've remembered the one just before as an n minus 1. We can throw this one away and keep this one. So we don't exactly undo f. We just remember the most recent thing before the most recent f. And when you put it in code, it looks like this. The shift is what we use in place of add 1. It takes a pair, and it takes the second part of the pair and adds 1 to it, but it also remembers the second part of the pair in a new pair. And then if we start out with 0 and 0, we shift it n times, then the second part of the pair as a result will be n, but the first part of the pair will be n minus 1. And then once you have sub1, you know how to write sub. It's just the same as writing add or multiply. So what we can see is from the lambda calculus, we can encode functions and local binding. Let turns into lambda. We can encode booleans, and we can encode numbers.